I am very pleased to introduce Ismael Gonzalez Yero from University
Hello,
of Cadiz. How are you, Ismael?
everything
I'm
is fine.
I'm happy
Hi, Ismail. Hi, Ismail.
to see you here again. Thank you so much
Thank you for inviting
for
me.
accepting this invitation from Novosibirsk. Ismail is a professor at the University of Cadiz in Spain and is famous in graph theory, especially metric graph theory and domination theory. And now we want to talk about, I think, efficient open versus efficient closed domination graph. Please, Ismail.
So, in this sense, I'm ready to begin my talk, in which I would like to speak about some, I would say, nice topics from my point of view of domination in graphs, which are that of efficient open and efficient closed domination, which are concepts, well, which are classical, I think, in the domination theory. This indeed is a work which is somehow old. I mean, it's something that I was doing a few years ago, but that I'm indeed interested in and into somehow continue this line, and I think that even deserve much the attention. So that's the point. That's the reason that I am speaking about it this talk. Well, first of all, I will comment probably on the definition of domination, but it also probably will not be necessary because you all are specialists probably on domination in graphs, and even this is a workshop on domination. So more or less everyone knows that it's dominating set, that all vertices of the set must be dominated by one vertex of the set. But now, efficient domination, what exactly is? I mean, we know that in the dominating set, we have the particular situation that every vertex which is outside of the set has at least one neighbor inside the set, the dominating set. But it could happen that the vertices will have different neighbors inside of the set. No? I mean, have one, some other one will have two, and so on and so on. But then one particular case will be exactly when we will have a dominating set, yeah, for which the closer neighborhoods of these vertices not only cover the vertices of the graph, but also they form a partition of the vertex set of the graph. It means that every vertex which is outside of the dominating set has exactly one neighbor inside of the set. And so in this way, I mean, I can do partition of the vertices with the center vertices are precisely the vertices which are in the dominating set. Yeah. I mean, if we have a D which is an efficient closed dominating set, it happens in this situation that the vertices of the graph G is equal to the union of the closed neighborhood and the intersection of any closed neighborhoods, any two closed neighborhoods, is an empty set. Yeah, this is for every pair of distinct vertices of the graph. Clearly, these efficient closed dominating sets are also known as perfect codes, and we can even find also only efficient dominating set without the word closed. And I think that there are a few other more names which are related with the same concept. But I think that the main are these two. And here we have an example. For instance, if we take this graph, which has this kind of tree construction, we'll see that the vertices which are in black, all these forms, right? This other one here, and these two, and this other one at the beginning. This is a dominating set, and it is also efficient closed dominating set because each vertex has exactly one neighbor inside of this set, and there is this partition. Whenever I will take these two here, then these two vertices are adjacent only with that vertex, and the other one with these two, and so on and so on. Clearly, not every graph has an efficient closed dominating set. You can find a lot of graphs which has no efficient closed dominating sets. But as we maintain would assume or would think, the problem of deciding whether a graph has an efficient closed dominating set is an NP-complete problem. I mean, it's not easy to know when we will have an efficient closed dominating set or no. Yeah, so this is a problem. And one particular situation is that when we have an efficient dominating set, closed dominating set, then the domination number equals the cardinality of such set. I mean, in this case, the domination number is equal exactly to this cardinality. And now, very related to the concept of domination, there is the total domination, in which the domination property is required not only but to the vertices of the set, outside of the set, but also to the vertices of the set itself, I mean, to the wall graph. I mean, set is total dominating set if any vertex of the graph is adjacent to a vertex of set S. Yeah? So all the vertices are dominated. And then, in relation with this, it would be normal to that the existence of efficient open domination. If there exists domination and efficient domination, that it should be normal the efficient and efficient total domination. That will be some efficiency. But now this efficiency needs to be somehow different understood. You will see that our the construction is a little changes later. So the idea is that now we will have a total dominating set in which the open neighborhoods of the vertices of this total dominating set not only covers the vertices of G, but also forms a partition of the vertex set. Yeah, I mean we have a D, which is an efficient dominating set, open dominating set. If the open neighborhoods, the union of all these open neighborhoods equals the vertices of the graph G, and the intersection of the open neighborhoods, yeah, any two open neighborhoods, their intersection is M. Yeah, this is for every pair U of B of distinct vertices of the graph B. Of course, this will mean that when we will have the vertices of the total dominating set, which is efficient, since they need to have one neighbor inside, it means that each of them needs to have inside one neighbor, but exactly one. So the vertices of the total dominating set will appear in a union of K2. Otherwise, this is not one. And all the efficient open dominating sets are also known as total perfect codes, the same notation of the other ones. And here we have an example. Yeah. You see that this tree, we take these two vertices at the end, they totally dominate this one, these two here totally dominate this on the other side, and so on, all the two vertices. You see, the total dominating set is the union of edges, I would say, pairs of edges, I mean, they form a matching in the graph. Well, perfect matching in this set of which is total dominating set. There's two vertices, two vertices, two vertices. No? And similarly to the case of efficient domination, then the efficient open domination also has the same property. That not every graph has an efficient open dominating set. And as you could also think, the problem of deciding whether a graph has an efficient open dominating set is an NP-complete. Yeah. And again, the same property. We have a set S, which is efficient open dominating set. Then the total domination number exactly equals the cardinality of such. Yeah. So these are the main definitions. And then these are indeed all the subsets. I'm not wrong. They are relatively old. And many people have studied these topics for different points of view. So one thing that we are usually doing, and the topic in which I work intensively indeed, is that of product graphs. I mean, I like very much the case of product graphs. And then we began to consider some of these problems for the product of graphs. Yeah. So in particularly, we were considering the efficient open domination in the product of graphs, because the efficient domination, the efficient close is more studied. So we considered more the efficient open. Yeah. Even so, there were already some studies. For instance, the direct product of two graphs has an efficient open dominating set if and only if both G and H have efficient open dominating set. This is a result problem. Esmeralda Hammer, 2008. And the idea, more or less, it can be relatively easy to understood because you know how is the structure of the direct product. I mean, in the direct product we have the crosses of the adjacencies. I mean, if two vertices are adjacent in one copy and adjacent in the other one, then there is this cross. So this means that when I will take two vertices here in one part and that they are in an efficient open dominating set, and two in the other efficient, then I do the cross and they kind of remain covering the same the open neighborhoods of them, and then we easily more or less get the situation. So this was already made it, and then we consider other cases. For instance, the lexicographic product. I mean, the lexicographic product of two graphs G and H has an efficient open dominating set if and only if one of these two situations happen. First of the one is that G is a graph without edges, I mean, the graph is empty, and H has an efficient open dominating set. Of course, this is somehow trivial because if G has no edges, what I have is several copies of the graph H. So then in this case, clearly, if H has an efficient open dominating set, so the union of many of them will work. And the other situation is that the G has an efficient open dominating set and H contains an isolated vertex. If it is the case, then I just consider this copy isolated vertex in H, and with it, this isolated vertex in H, since it is isolated, there are no neighbors in the same copies, so this vertex will dominate all the vertices in the remaining copies of G, since G has an efficient open dominating set, and everything goes more or less easy. So the lexicographic case was easy also, and the strong product also more or less easy. So we have the strong product of two graphs, G and H, and it has an efficient open dominating set if and only if one factor is a graph without edges and the other one has an efficient open dominating set. So it's something somehow trivial also because there is no edges in one graph, so nothing to do. Now, for the Cartesian product of two graphs, it has an efficient open dominating set if and only if, well, we don't know exactly. So the main reason for that comes from many problems that we know that in domination, that in the case of the Cartesian product is very hard. Well, indeed, I see that this mistake here. This symbol should be the square or not the like in the case of the strong. I mean, the Cartesian product is with a square. Yeah. So what we were doing then is considering just some examples of Cartesian product. And I will enter a little deeper in the case. For instance, we know the definition of Cartesian product. In this one, for instance, the vertex set is the Cartesian product of the vertex sets of the graphs, and they are adjacent if they have the same component in the first if the first component are equal and the second one form an edge, or vice versa. Second component are equal, or and the first components form an edge in the corresponding graph. So it was somehow suspected that the case of domination for the Cartesian product will be not easy. We, for instance, have the missing conjecture, which we know that it's very hard. It's very open problem. So we focus then in the case of prism, the Cartesian product of a graph with K2 on. And we will see that even in this case, it is already not that easy task. So to do this, we were seeing that, I mean, what we have is the copy of two graphs. I mean, I have one graph and a copy of the other graph, and then the corresponding edges in the positions corresponding to each of the vertices of the graph. Yeah. So it means that if we are looking for an efficient open dominating set, we have some possibilities. I mean, remember that an efficient open dominating set is formed by the union of K2s, I mean the edges. So if we are looking for an efficient open dominating set in the prism graphs, it could happen that the edges are horizontal, I would say, or vertical, or in both directions. I mean, if all of them are vertical, it means that they all of them will be. We can probably draw some figure here. I mean, it could happen something like, since I have my graph here and my other graph in the other direction, if all of them are vertical, I mean, like all the edges of the efficient dominating set will be in such way, it means that they should have some neighbors here, they should have some neighbors here, and they should have some neighbors here. But then it means that these vertices which are here, they cannot have common neighbors. In situations like that cannot happen, because then it's not an efficient open. Because the efficient open dominating set is only like that, this vertical situation. Only vertices which are here, yeah, they form vertical situation. And on the other way side, if we have uh, that the edges which are in the efficient open dominating set are horizontal, like that, yeah, then this will mean that these vertices will have some neighbor here, and then this part here cannot be in the efficient open dominating set. I mean that these vertices will be somehow alternating. I will need some not to take here. I cannot take some here. I cannot take here. And then I can take this part and so on and so on and so on. So I need to have some kind of efficient domination in the graph G, but that will have some possibility of alternating. In one part I take one, in one part I take the other, so on and so on. And I can have, of course, both the combination of both. I can have part horizontal, part vertical. Yeah? So with this in mind, we were observing that we need to define some family of graphs, which we call zigzag graphs. Yeah. What is a zigzag graph? Well, it's a graph which is having this property that, well, here is an example. So it's a graph of order at least 3, and in this graph, it will have a set of edges, which I will call E prime, yeah, and the edges are denoted in this way: EI, E2, E1, E2, E3, so on till EK, yeah. And there will be some situation that in the neighborhood of the vertices which are belonging to these edges, I mean, EI is UI BI. So the intersection of neighborhood of UI and BI is empty. And the distance between these any two edges of this set of edges is at least 2 for every pair. Yeah? Also, if I take any vertex which is not in any of these edges which are in this E prime, then there exists a unique uh, uh, S T such that S is different from T, and the distance between W and this ES is equal to the distance between W and this ET, and it is equal to 1. Yeah? It means that, for instance, I can take here this edge which is here below, and this other edge which is below. Yeah? These two edges are at distance at exactly 2 in this case, and these 3 edge vertices which are here, they are at distance 1 to this one and 1 to this one, and so on and so on. Yeah? And finally, for every maximal sequence of distinct edges that I will take in this set of edges here, with the distance between them is equal to 2 modulo this number s plus 1, then this number r, yeah, must be an even number. I mean that, which is a maximal sequence, for instance. Or all these black edges which are going outside in this kind of cycle, yeah, they form a maximal sequence. I mean, as you see, there is not an even number. I mean, 2 here, 2 here, 2 here, and 2 here. Yeah. If I consider, for instance, these two, this is also a maximal sequence, and they are 2. Yeah. If I consider here this maximal sequence in the center, they are also 2, and this again a maximal sequence. Yeah. Notice that this case, for instance, these 4 edges which are here outside, together with this one in the middle, is not one maximal sequence. Yeah, because here the distance between these 2 edges is 2, but the distance between this edge and this one is 3. You see, 1, 2, 3. So this is not the maximal sequence. All the maximal sequence are this one which are here, this one in the middle, and this. So if this happens, then I have the possibility to, I would say, do this exchange that I will take one in one side, one in the other, one in the other, one in one copy, one in the other, and so on and so on. And it will be possible to construct one efficient open dominating set. Yeah. I mean, for instance, we have a G with Cartesian with K2 when G is a zigzag graph. Is this one. I take a one copy, I take another copy, and the corresponding edges. Notice that I have not drawn the edges which are joining the vertices from the two copies. I mean, there should be one edge going from here to here, or one other one from here to this part of the other one, and so on and so on. Every vertices which are in the corresponding place, position, then they must be joined by an edge which is corresponding to the K2 problem. Yes. So in this case, as you see, I can say, and I can take this alternating sequence. I mean, here the efficient open dominating set, remember, was all these black edges. Then I just take here. If I take this edge here on the top, then I cannot take it. If I don't take this edge here on the top, then I can take it below. And so in this way, you construct, which is a set, which is an efficient open dominating set in the this Cartesian product of K. Yeah, and in this case, as you see, all the edges are in horizontal way. In the horizontal because they belong to the copy of the graph G. This is drawn kind of vertical, but it's horizontal edge. And they are in the copy of G. Yeah. So this is one case, one situation in which we have this construction. Now, this is one thing. If G is a zigzag graph, then G Cartesian K2 has an efficient open dominating set. But it remains something more, complete characterization of all graphs that have efficient closed, that has this efficient open dominating set in the Cartesian product of K2. And this is related with this efficient closed domination in graphs. I mean, as I was drawing here, well, the case in which the edges are vertical, I mean, I take one here and one here, and one here, one here, this is related with efficient closed domination. I mean, when we have a graph G which has an efficient closed domination set, dominating set, I mean, it's an efficient closed domination graph, then the Cartesian product of K2 has also an efficient open set. I mean, I just need to, if I take one graph, this graph, I have one efficient efficient closed dominating set. It has some neighbor. And then I have this other vector which has some neighbor also. Then the union of the copies of these ones is an efficient open set because the things will be going in this direction, and I have here efficiency. So with this in mind, then we say, okay, we have this, the zigzag graph, and we have this other case in which you have efficient open. This case, yeah, we have this also this case. And then what we call one perfect zigzag graph. Yeah. So one perfect zigzag graph is a graph which is obtained. We take H1 is an efficient closed domination graph. I mean, one graph which has an efficient closed dominating set on this P. We take H2 is a zigzag graph, yeah, which has zigzag set, this one which we have here, this set of edges. And then one perfect zigzag graph is a graph which has vertex set, the vertices of H1, union the vertices of H2, and the set of edges is all the edges of the graph H1, all the edges of the graph H2, together with one set of edges E3, which is joining some vertices of this both H1 and H2, but cannot be anyone, can be some of them, which are, so we can have edges of style XW, where X is in the set of vertices of H minus the efficient closed dominating set, and W belongs to the vertices of H2 minus the vertices which belong to the zigzag set of, I mean, the vertices which are the edges in the zigzag set. So vertices which are not involved in the domination set. So if this is, we define a graph this way, I mean, all edges of H1 or edge of H2, and for every vertex which is not the efficient closed dominating set, and every W which is not in the zigzag set, we may insert an edge between these two vertices. Or no, maybe we don't need to add. I mean, there could be some edges. So with this graph in mind, then we were able to prove that the Cartesian product of a graph G with K2 has an efficient open dominating set if and only if the graph G is a one perfect zigzag graph. I mean, the graph needs to have one part in which we have this zigzag, and in the other part, there will be this efficient closed dominating set and some edges between them. If this is happening, then we have the situation control. And we have some, we can always be constructing one efficient open dominating set. Notice that when we have this one perfect zigzag graph completely, there will be edges which will be horizontal and there will be edges which will be vertical. I mean, both of them. So that's took relatively some hard work to make it, but it was nice because it was, I mean, it is possible to follow the ideas and the technique which were used. Indeed, the technique which were used here were after used by some other authors to consider the case of G with any complete graphs. Then some ideas were also applied. It was possible to study also G with any complete graph, and even I'm thinking that graph with a bipartite, complete bipartite graph, but I'm not so sure. So another thing is to consider some other cases of Cartesian product graphs, like I don't know, the grid graphs, the torus, and so on and so on. So I mean, consider some different styles. There are partial results on each of these topics. I will speak about that later. So one other thing that we were then considering it was the following. I mean, we have efficient open, efficient close, but we were wondering, is it possible that there are graphs which will have both things? I mean, we know that not every graph has an efficient open dominating set, and not everyone has an efficient closed dominating set. But is it possible that there will be graphs which will have both things? Yeah, and it is true. I mean, there are graphs which are having both things. For instance, this example. If we consider this tree, which is something similar to the one I represented before, we see that the vertices in black form an efficient open dominating set. All these spaced edges, which are here, and also the vertices which are large sized vertices, they form an efficient closed dominating set. I mean, all these ones form an efficient closed dominating set. And you will see some particular case situations. There are vertices which are belonging to both. Yeah, there are vertices which are belonging to one of them, like for instance, these two are only in the efficient open, in the efficient close, and there are other ones, these bolt, which are only in the efficient open. So there could happen many situations. And there are other ones which do not belong to not to the efficient, not to the open in any case. So there are these other kind of cases. So the question was, are there several graphs having this property that they have both of them? And how much difficult is to decide whether a graph has this one? Well, if it is difficult to find one or the other one separately, it would be somehow normal that the union of both of them will be also very difficult. Yeah. So we call them efficient open closed domination graphs, the EOCD graphs. So are graphs that are having an efficient open dominating set as well as an efficient closed dominating set. And then we were considering several properties. For instance, first we were observing that when we have these graphs, which has an efficient open dominating set D and an efficient closed dominating set P, then the vertex set of the graph can be partitioned in this way. I mean, we have the intersection of D and P, the set D minus P, the set P minus D, and the remainder of the vertices union minus the union of them. So the graph is looking always like that. Yeah. If we have the intersection of D and P, which are black square vertices here in this part, there is there is an arbitrary number of neighbors in R. They have an arbitrary number of in R, but they have a unique neighbor of D minus P, and they have no neighbors in P minus D. According to here. The vertices which are in P minus D, which are a white square, I mean all these ones here below, they have an arbitrary number of neighbors in the set R, but they have a unique neighbor in D minus P, and they have no neighbors in the intersection between. This is more or less the structure that you see. And D minus P, these the black vertices, they can have an arbitrary number of neighbors in R, and they have either a unique neighbor in P minus D and a unique neighbor in D minus P, or a unique neighbor in the intersection. I mean, something like this here. One. Yeah, they can have either this one or the other one, or a unique neighbor in both of them. And the vertices which are in the set R, which are white vertices on the right, they have an arbitrary number of neighbors in set R. Of course, they can have any neighbors here. And they have either a unique neighbor in P minus D and a unique neighbor in D minus P, or a unique neighbor in the intersection. Yeah. So with this structure was helpful after. These are properties, I would say, that were helpful after to construct some sets and to study these graphs. And for instance, we know about this connection which exists between domination and total domination. Means that the total domination is always bounded between domination and 2 times the domination. There are several studies concerning this characterization of these graphs. Then, for instance, when you have a graph which is an efficient open closed domination graph and has empty this intersection between D and P, then the total domination equals the domination. And when we have these graphs and they have empty this quantity P minus D, then the total domination equals 2 times the domination. Yeah? This allows us to get this structure. And the other question was related to how difficult it is. Well, I mean, if we have a graph, is G an efficient open closed domination graph? Well, this problem is empty-complete. And to do this, we use a reduction from the 1 in 3 sub problem. Yeah. So we have a Boolean formula. Well, any variables and any clause. And the thing is that is there a satisfying truth assignment of the any variable so that each clause has exactly one true literal? On this particular case of 3 sub, and we were using that to construct to prove the complexity of this problem. Yeah, this reduction, which is relatively also nice to see because we are using some graph which is kind of it's a graph which has some structure that is similar to the one of this prism, I would say, because it has possibility to alternate from one part to the other one, so that then we can get some ideas. And then what we began with is consider some graphs which we can study the properties of being efficient open or closed domination graphs. There are some graphs in which is already known that they have efficient open dominating set. There are some which is already known that they have efficient closed dominating set. And the question is if they also have if they are also efficient open closed dominating set, or they are not, or something like that. And then we began, for instance, with the case of Sierpinski graphs. Sierpinski graphs are graphs which are it's a construction which is made somehow like over here. We begin with a complete graph. For instance, this is K4, then S41 is a graph in which we begin with K4, and then for the construction of S42, the second step, I would say, in the construction of the Sierpinski, we take as many copies as the order of the complete graph is. C4, K4, then we need 4 K4. And then we join this, I would say, the corresponding vertex in the copy, which is here. For instance, if this is the first copy, I join the vertex which is in the copy in the position 4, in the copy 1 with the vertex which is in the position 1 in the with the vertex 1 in the copy 4. I kind of exchange the labels. So this is the vertex 4 here, yeah, the position 1, then this is the vertex 1 in the position 4. And then I do this more or less like I construct. This is the vertex here, which is in the position 3 in the copy 1, then I join it with the vertex 1 in the copy 3, and so on and so on. Yeah. And then I repeat the same process. Now I copy this S for 2, 4 times here, 1 time, second time, third time, 4 times, and do the same. I add the edges here according to the position which they are. This is the vertex here, which is in the corner, in the position 3, yeah. The third vertex in the first for the first copy, and I join it with the first vertex in the third copy. Yeah. So I construct, this way I can construct all the graphs. And I can do the same for a complete graph with 3 vertices, 4 vertices, 5. Yeah, the formal definition is here, but I don't want to enter too much on it. So better simply to explain it in such a way that is very constructed. Well, these graphs are relatively very known and very popular. Many people study about it. So the question is on whether this graph has an efficient open closed dominating set. Then they were already studied. It was known that this graph has efficient open dominating sets in some situations, that they have efficient closed dominating set in some situations. So the question is whether they have also efficient open closed dominating set. So for the first case, when we take the smallest case, K1 is just one vertex. Yeah, it's not an LCD graphs. I mean, it can have probably efficient open, but not efficient close, and so on. Then the other one is S2 n, which is isomorphic to a path of order n to n, and this always has an efficient open close. It is always an efficient open close domination. We can have efficient open dominating set and efficient close dominating set. And this other case is not an efficient open close. So it was remaining only the other cases when P it was at least 3. Yeah. So if we consider P at least 3 and N larger or equal than 2, then this Sierpinski graph P is sub P sub N is an efficient open closed domination graph if and only if the value P is even. I mean, if we are doing the construction with a complete graph of order N. Here, for instance, we have example. I mean, we know that this is not the case because we already have it here. This P sub 1 is isomorphic to KP. I mean, the first step is not an efficient open closed domination graph. It's never because it is efficient open. It is efficient close, but it's not efficient open. But now, when we pass to the second step, we can always do this construction. I mean, we take these two vertices, yeah, they form an efficient open dominating set because this dominate all here, this dominate all here, and this dominate all the other part, and so on. And for the efficient closed dominating set, we take all these corners. And then this is an efficient closed dominating set. And now for the second step, we cannot use these 4 elements which are here in the corner because they will be in the corner and they will be adjacent to the other corners on the other side. But then we need to change a little. So, I mean, these vertices which are here, these 4 in black, this is no problem. I can keep the structure. I mean, just put these two, these two, these two, these two, and each of the construction I use the same. And since these vertices which are here, they will have neighbors. When I will do the second step, then will be always the same. I can always have. But these 4 I cannot. So I need to take another one. But I can take, for instance, these 3 here, yeah, these 3 here, and then this also 3 here, and this in the first, in this one, then I take 4 elements. Notice that this is covering and dominating all this part, all this part, all this part, and each of them is dominating one of these other copies. This is dominating this vertex, this other on the other part here, and this on the other part here. It remains to dominate only one vertex here in this corner, but this is dominated by this on the other side. Yeah. So this is the reason that in one copy of this construction, I have 4 vertices for the efficient closed dominating set, and in the remaining ones, I have 3. And with this construction, I can go to further steps, and I will always have possibility to construct set. Notice that here it is only one corner, so this will not affect the same construction, because then I will always have the fine, I would say. So in this case, the reason was that an efficient open dominating set is an Sierpinski graph is an efficient open closed domination graph if and only if the value pays even. I mean, if the complete graph that I'm using to construct this is even. I mean, if it is odd, then I cannot construct this situation. So there were several other few other more results on some graphs about this efficient open closed domination graph, but not many. If I am not wrong, I have not seen too much more about it. I mean, I haven't seen any continuation of this work in which graphs which are efficient open closed domination graphs are considered. For instance, what I was telling you that when we consider the torus graph, it is already known that this torus has an efficient open dominating. Well, this is some conjecture, I would say. It has an efficient open dominating set if and only if both R and T are equivalent with 0 modulo 4. Yeah. And in the first work where we studied the Cartesian product, there were made several things. I mean, we were considering, for instance, some cases in which only probably one of these R or T was equal to C4, or in which one of them was even and the other one yeah, I think that only C4 with somebody more and so on, a few things. So there are some partial results of this, but not all of them. In the case of the cylinder, I mean the Cartesian product of a path with a complete graph, path with a cycle, then it is known that they have an efficient open dominating set if and only if either one of these situations happen. I mean, this number problem. With one of them is equivalent with 0 modulo 4 and the other one equivalent with 1 modulo 2, or the T is not equivalent with 0 modulo 4 and T is equivalent with 0 modulo 3, and R belongs to 2 T minus 1, or one of these. T equivalent with 1 modulo 2 and R is equal to T minus 1, or T is equivalent to 2 modulo 4 and R is equal to. As you see, there are several situations that would happen here. So this is even doing that. The problem is probably harder to consider in the case of the cylinder than in the torus. One problem is that in the torus, I mean, the graph is completely, it's a cycle in one cycle, and we can more or less control that every vertex will have what will happen because there is a continuation. I mean, all the vertices are of degree 4. This is also possible to see. But in the case of the cylinder, there are borders. I mean, there are vertices in one side and in the other one that are having degree 3. This is doing some complication. Yeah. And this is that, okay, we have proven that the cylinder, the case of the order of the path is 2R plus 1 and the cycle is C4, then it has a total perfect code, sufficient open dominating set for every value R and T. Yeah, largo equal that. And there are some other specific cases which are smaller cases, I would say. And with this, I'm finishing my talk. It's a little earlier than I suppose, but I think that is quite enough. And then you can ask anything that you will like, if you will.
Okay, thank you so much, Ismail, for your nice presentation. Very nice result. Is there any question or remark, comments? If yes, please raise your hand. Ismail, let me to ask a question. Uh, whether efficient open or closed dominating set in a graph is a unique dominating
No, I don't think so. Not necessarily. I mean, there could be some cases in which they are unique, but of course there are some which is not. Simple case, I would say, for instance, when we have a cycle. If we have a cycle C3n, it has an efficient closed dominating set because you need to take only vertices and the two neighbors is always covering all the. But then, I mean, you can have a lot of them. You just need to switch to the neighbors and that's it. And efficient close, of course, is the same. Efficient open is the same. I think that not necessarily unique, but probably it's interesting to see such kind of construction,
Yes.
whether we have unique.
Yes, I think this is a good question that which kind of graph have unique efficient.
Yeah, it is definitely a good question, yes.
And I saw that you said about their product. I don't remember whether you said about the chronographs, whether if we have G and H have a efficient closed dominating set, whether their corona have or not.
Whether which product? I don't.
Corona. Do you know corona?
Corona. Oh, in the case of corona, okay, the corona it is a graph in which there are some hanging from it. So it somehow, I mean, if we have an efficient open dominating set in the graph, I mean in the graph which is below the copy of the, I mean G corona H, if we have efficient open in G, then there will be efficient open in the corona definitely. And the same if it is an efficient close in the corona, in the graph G, then there will be also a efficient close in the. No, I'm wrong. Because the vertices which are outside, adjacent to the vertices which are not in the dominating set, they are not dominated. Then I need to have something there.
Yeah.
Okay, so then, and all of them will have a common neighbor. So yeah, probably it's interesting to consider it. Maybe I think that's probably not that hard, but makes sense to consider it because then, I mean, if I have this construction, I mean in the corona, I have this graph, G, no? My corona here. So a simple case, I have this vertex which is dominating these two. It is an efficient close, yeah. And then with this, I remain copying, dominating this and also this, yeah. But then I need to have some here. And this vertices here has a common neighbor with it. Yeah. So as soon as I will take a vertex here, then this will dominate this also. And they will have empty intersection, the same intersection. But then I don't know whether I can construct somehow something. Because probably I could find, yeah, I could find some here that will dominate here this and this, but this will not be dominated. Maybe, I don't know. Maybe it's possible to get something.
Okay, very nice subject idea. Very good result you had.
Thank you.
Thank you so much. Is there any question? I see Ismail Sahul. Maybe he want to present the next presentation. Maybe. Do you have any question, Ismail Sahul? Have it?
Yeah. Good evening, sir. First of all, good evening to congratulations to Dr. Ismail from Spain for a nice presentation. Really. Sir, I hope you might be aware of the concept of two packing sets in graphs, which means a set where the close neighborhoods of any two vertices are disjoint mutually. So n of closed u intersection n of closed v is equal to empty for any two distinct vertices u and v in the set. So two packing set. So,
Yeah, of course. When
yeah,
we
so-
have if you have a packing set,
yeah.
um,
So which means the efficient, I understand, I may be wrong, please correct me if I am wrong. So I understand by efficient dominating set, do you mean a set which is both a dominating set and also a two packing set? Am I right, sir?
yes. It's
Because two packing
yes, efficient open is a dominating set, which is a two-pack, yes.
so efficient closed dominating set is a set which is both a dominating set as well as a two packing, right, sir? So you are looking for the existence of such a set which has two properties, domination and as well as two packing.
Mm.
And from the two packing, we can have a square of a graph, G square, where the vertex is the same as that of G. And in G square, two vertices are made adjacent if their distance is at least 2. I'm sorry, at least 3. So a dominating set in G square, which is also a clique, will be a efficient dominating set in the underlying graph G. So looking for a efficient dominating set in G may be equivalent to looking for a clique dominating set in G square. Am I right, sir?
Yeah. It sounds fine. Yes. I think you're right.
So
maybe this is written somewhere. I'm not aware of it.
Okay, so what I feel, this might be opening a new to look the problem into the different angle of existence of efficient dominating set. That's what my
Yes.
suggestion.
Yeah, definitely.
Thank you.
Thank you.
Thank you,
Okay,
sir.
thanks. Thank you so much, Ismail,
Thank you, sir.
for your nice question and remarks. Okay, is there any question or remarks? If no, thanks again, Ismail Yero, for nice presentation. Thank you so much, Ismail.
Ismail, thank you so much for your nice presentation.
It was my pleasure.